Okay, so first I would like to thank the organizers to give me this opportunity to to explain some results we proved and in this tropical seminar. So essentially, I have to say that I learned this, the first time I know this tropical geometry was from a talk by David Speyer 8 years ago in 2012 in Paris. And then I never thought that I would give a talk on this topic and at that time. And suddenly our work on representation theory just meet part of the tropical geometry. So now in this talk, I want to share you some results relating tropical flag variety. Okay, so let me start. So, okay, now first I want to say something about a short history about my own knowledge on the tropical flag varieties. It's very interesting to say that the first time we started to consider this tropical flag variety was in 2016 in July at Frankfurt. So it's very nice to give this talk in Frankfurt because it comes back. And this was a summer school. If I think at least Laha was there, I don't know whether others were there. And there was a very nice sunny afternoon, let's say afternoon, and we had some lunch together outside, and we were talking about this tropical flag variety together with Bernd Stumfels. And then 1 year later, Laha, Sarah, Kalina, and Fatime, they wrote wrote a paper on the first study of this tropical flag varieties. They called computing toric degenerations of flag varieties. Essentially, in this paper, they first give a package of computing these tropical flag varieties, and in the small rank examples like flags 4 or flag 5, they gave many weight vectors such that this initial part associated to this vector of the Prequel ideal defines the toric variety. Okay, so now I have this paper by hand. You see, so you can recognize that this is your paper from the title. And then if you turn off the paper on the last page, you see some dense thing. And all these dense things are some numbers, some magic numbers. You plug in these numbers, you get toric varieties. Okay, and then I look at these numbers. I have no idea. These are, for me, random numbers. The question I ask is, in general, how to find these weight vectors, how to find these numbers. Okay, and they said, okay, computer will tell you, but okay, computer will tell me, but it will only tell me up to flag 5 or flag 6. And then we thought about a harder question. How we find these weight vectors? If we could find some defining inequality of the maximal cone in the tropical flag variety, definitely we will get these weight vectors easily. So, and now we ask this, we ask this harder question. I think this kind of question, up to my knowledge, is quite rare in the tropical geometry because I don't know whether you are expecting to finding explicit defining inequalities of maximal cones in the tropical flag variety. And maybe people think we are crazy. And the goal of this talk is to tell you that really we can give inequalities defining one maximal prime cone. I will define what is maximal prime cone later in the tropical flag variety of type A complete. So, and this is the goal of this talk, is to explain this result. And this result is first proved in the joint work with Evgeny Feigin, Fourier, and Igor Makhlin in 2019. But the proof was purely representation theoretical. And I would guess that it will be very hard for you to understand all these details. And now today I want to explain some I want to give a different approach to this problem using essentially only Grobner theory, toric variety, or valuation, Newton-Concave body, Chovansky basis, all the things you know very well. So I want to build this bridge between representation theory and the tropical geometry, and I hope I can make it today. now I want to start, and everything starts with a dot. So you all know this phrase from Kandinsky. Okay, where is the dot? Everything starts there. The dot is in a joint work with Fourier and Marcus Reineke. So essentially, the motivation of our work was we want to study some quantization of the PPW filtration. So PPW filtration is something from representation theory. And if I rephrase what we did in the tropical or Grobner language, which means that we essentially give a dot, a point, in the this point hits the interior of a maximal dimension, a maximal prime cone in the tropical flag variety for any n. But this is with a different language. This language was quiver representation and degeneration of modules and all this. And then later, the same dot was found in joint work with Theo Backhaus and Fourier. We found such a dot exists in symplectic world. And then starting from this dot, we want to get dot, line, plane, and all these abstract things. And then in this 2019 paper with Evgeny Feigin, Fourier, and Igor Makhlin, we can extend the dot to get a cone in the representation theoretical point of view. And then later, another paper, we connect this cone to the quantum world. This paper should be here because it was finished in 2018, but we all forgot to put it on archive. So it was appeared later. And then recently, it was found that such a cone also exists in the categorical world because we can, from some category, we can recover this cone as some very important skeleton. And today, my goal is to explain this work of FFFM in a different language without representation theory. So as Martin suggested, I will try. Yeah. Okay, and today's keyword are Grobner theory, maybe Newton or Konkoff idea, and Hovansky. Okay, now I want to start with a rough version of what I want to explain. So, okay, the precise result will come later. Now I just want to give you some intuition about what I want to say. So essentially, I want to explain you that there exists, there's no S because there exist two things. First is an explicit simplicial cone. I call it C. This we know the facet. And second is an explicit linear bijective map, alpha. Alpha is from this cone C to the tropical flag variety, such that it is bijective to its image, and the image is exactly a maximal prime cone in the tropical flag variety. And this trop FLN+1 is the tropical flag variety with respect to the Prequel embedding, so I will define it later. Okay, so this is the rough version. And now you see what I need to tell you is what is this cone C and what is this linear bijective map alpha. And that's the two parts of the talk. Okay, I will give you some rough idea about how this connected to the Lie theory. Okay, let's look at this small picture I draw here. So in the tropical world, essentially, we look at flag variety as subspaces in the Grassmannian product of Grassmannian, such that they have this inclusion condition. One is included in the other. And when look at this one and look at the Prequel embedding and look at the Prequel embedding and when take the ideal and when tropicalize it. And in the Lie theory world, we are not really want to use this linear space description. We want to look at it as a homogeneous space as G mod B. B is the Borel subalgebra because
Quick interruption.
Yeah.
Is your fan structure the Gröbner fan structure from the Prequel embedding?
Which fan structure?
The one you're using a cone of, I guess.
cone, the cone, I will explain this later. It's there. It is some Grobner theory, but it is a different, completely different Grobner theory than the tropical flag variety. Or I will do this later. Okay, and the Lie word is come from this homogeneous space because GLN acts naturally on the flag variety, and you take a standard flag, you take the stabilizer, and then you get this connection. This is isomorphism as a projective variety. And today, my idea is to go from in this direction. I will start from the Lie word, and then I will go to the tropical word. And then the outline of this talk is I will explain what is the cone C, what is the linear projective map alpha, and what is the result. And if time permits, I will give you many remarks. And also, I want to say that this is a work in progress, so I will only explain you the part which is definitely done. And there are some work in progress, and there's some other results, but I think I'm not willing to say that today. Okay, so the essential idea of this construction of this link is via an object called birational sequence. This birational sequence is defined by Ghislain Fourier, Peter Littelmann, and myself in 2017 in a work to unify all the toric degeneration of flag varieties. Okay, and I will explain first what is this birational sequence. And but for that, I need two, as usual, fixed sum notation. And I hope these are everything I need from, I should not say this is a Lie theory, but it's a very elementary group theory. And I try to make everything simple by fixing only type A case. And I will only consider some example without going too much into representation theory. Okay, now in type A, my group is SLN plus 1C. I use n plus 1 to simplify notation. These are determinant 1 matrices. And then its Lie algebra is the Trislist matrices. And I fix my favorite Borel, which is the upper triangular matrices in J. And then I fix my unipotent lower triangular matrices with 1 on the diagonal. You just enjoy this picture. You don't really need to read the thing. And then I fix in the Lie algebra my favorite Gardin, which is given by the diagonal matrices whose sum is 0. And then I will define this epsilon I in the dual space of these diagonals, which are exactly taking the ith entry of the diagonal. And then in the Lie theory, one of the most important thing is you have these simple roots. The simple roots are just epsilon I minus epsilon I plus 1. They form a basis of H star. And then I will denote all these positive roots by delta plus. The delta plus consists of alpha ij. This alpha ij are the sum from alpha I to alpha j. And how this might be a bit abstract for people not working on Lie theory. And now I will tell you that you can write them really using matrices. So for a fixed alpha ij, a positive root, I will choose a root vector, f alpha ij. It is in the vector space generated by this matrix entry. Here, I will say that this Eij, right here, this Eij, these are the elementary matrices. These are matrices almost everywhere 0. There's only 1 on the Ij entry. So I choose some element in the as called root vector. Example comes later. And then for this beta to be a positive root, I will define the root subgroup. The root subgroup is that you take this matrix and then you take the exponential of it. This is called the root subgroup. This guy is inside of my unipotent U minus. And then I will need this notation of big N. The big N is exactly the number of elements in my number of positive roots and it's the dimension of the unipotent, and it's exactly n plus 1 choose 2. It's just n choose over 2. It's just n choose 2. Okay, that's, I think, all I need for the from the least theoretical part. And now I want to introduce you the first important notion of the talk. It's called a birational sequence. And what is a birational sequence? It is a sequence of positive roots. And these positive roots are not necessarily distinct. It could be, there could be repetition. This sequence of positive roots is called a birational sequence. If the following multiplication map is birational, what is this multiplication map? So here I start with u minus beta 1. I told you that u minus beta t is this exponential, the image of this exponential. So I take these root subgroups, and then I just, all of them are in u minus. And u minus is a group. I can multiply them together, and this is a multiplication map. So I take exponential t1 f beta 1 and tn f beta n, and I just multiply them together. And I call this sequence a birational sequence if this multiplication map is birational. So this definition essentially motivated by the Newton-Alchenkopf theory. Okay, now let's do one example. This will be the running example of today's talk. I will take some sequence I called S3 for some reason you will see later. This S3 is the, here what I look at is the group SL3 or the Lie algebra SL3. And my S3 has 3 roots, alpha 2, alpha 1, 2, and alpha 1. So first, as I said, I need to fix my f, this root vector. I take my f alpha 1 is the matrix with here this 1. And I take my alpha 2 is the Euro matrix here. And I take my alpha 1, 2 is the matrix here for minus 1, 0, 0, 0, 0, 0 here. This is my choice. And now what is the exponential? Then I want to explain you what is exponential t1 f alpha 2, exponential t2 f alpha 1, 2, exponential of t3 f alpha 1. So you see that this order I choose is exactly the order here. And if one do this matrix multiplication, you will get a matrix. I will write here as I computed. If you trust me, you will get this matrix. This one is in U minus because it's the lower triangular matrix with 1 on the diagonal. And it's very easy to see that this is the birational sequence. This sequence is birational because you can find the inverse map. You can easily factorize this matrix. So, and then this one is a birational. Okay, I hope this should be clear. And now in this talk, I will only consider the following kind of birational sequence. And of course, you can consider birational sequences in general, but for this talk, I will only consider this is.
Quick interruption, another
yes?
question. How is it possible for the map to be birational if some of the roots are repeated?
Yes, for example, you take alpha 2, alpha 1, alpha 2, then you will get not an isomorphism, but a birational map. Yeah. And you can take a reduced decomposition, and then you take the simple roots associated to that. Then this is the Bott-Samuelson desynchronization. You will get a birational map. So, and I don't want to talk too much on that direction. So now in this talk, I will only concentrate on this birational sequence. I will explain you this birational sequence is the extension of this one. So I start with alpha n minus 1n, alpha n minus 1, then alpha 1n, 1n minus 1, 1, 2, and 1. This is my birational sequence. I will only consider this one in the talk, although some results will be true in general. And then I will give different indices to make some later results easy to describe, I will call them beta 1, beta 2 until beta n. And next, I will, because I want to know what's the relation between beta and this alpha, I will write beta k is, I will write these positive roots into the simple roots in this ak1 to akn. Okay, this is my notation. And now let's go, next step is I want to associate a Grobner theory to this birational sequence. And this will give us the cone C. And what is the Grobner theory? This is the Grobner theory from vector partitions. So I think you all know this topic, so I won't, I will only explain you the construction. Okay, so for the vector partitions, I will consider vector partition associated to these vectors, beta 1 to beta n. So which means that I will consider a polynomial map. This is my polynomial map from x1 to xn, this polynomial ring, to another polynomial ring, which maps xk to s1 ak1 sn akn. For example, I will, on the right-hand side, I will at the same time do the example, is my running example S3. So this, in this case, x1 go to S2, x2 go to S1, S2, and x3 will go to S1. Okay. It's just, I write alpha 1, 2, like alpha 1 plus alpha 2, I look them as a vector and I consider vector partition. And then from this polynomial map, the vector partition is to understand what is the kernel of the polynomial map. I call it I. This I is a binomial ideal. So this is the purely a toric problem, as you know. Okay, so now in this case, the I is exactly, because this case is very easy. So you're gonna get this principal ideal generated by x1 minus, x1, x3 minus x2. And now let me fix, because I want to do Grobner theory, I need to fix some ordering, total ordering, or monomial ordering, whatever. And I fix my favorite lexicographic ordering. Of course, you can choose arbitrary another ordering, but today, for my purpose, I only fix everywhere the lex ordering. And maybe if time permits, I will tell you about more orderings. Okay, if I fix my monomial ordering, the Grobner theory tells me that there exists a unique reduced Grobner basis of the ideal I. And this reduced Grobner basis is of course a binomial ID, it consists only binomials. I will write them in the following way. I write them as xai minus xbi, and aibi are some tuples to the n to the n. And I will let xai to be the initial part. Like in this case, x1, x3 is the initial part. For the initial, I always take the max in here. So because I always confused by different notations, mini-max, but here I fix my max. Okay. And then once I have this reduced Grobner basis, I can have the Streeting law. This reduced Grobner basis is essentially telling me what is the Streeting law. And from the Streeting law, I want to get some polyhedral information. And this is exactly the Grobner cone, which I think it's called Grobner cone, to my knowledge. And what is the definition of the Grobner cone? It's just all the weight vectors such that this one, the degree, the W is the weight. So the W degree of this one is larger than the W degree of that one. So this W degree tells you how the standardness mean in the standard monomial theory. Okay, now let's look at this, my running example. And for this example, C of larger of I, it's very easy. It's just W in R3, because I have 3. And W1 plus W3 is larger than, strictly larger than W2. Okay. So I get a cone from this vector partition problem. Okay, now I want to state the main result here. And before stating the main result, I need some new notation to simplify to let you understand what does this theorem mean. Otherwise, it's too hard. So the notation is the following. So if beta k, this root, is some alpha ij, then remember that here I have w is a vector in Rn, so it is indexed by the way this root beta k, 1 to the n, and I will write wk to be wij if beta k is alpha ij. So what does this mean in example? So in this example, I will write I have W1, W2, W3. W1 corresponds to alpha 2, this one plus alpha 1, 2. This one corresponds to alpha 1. So I will write W1, W2, W3 as W22, W12, W11 to record what are the roots, what are the degree on the roots I want to give. Okay, now that's all. And now it looks quite simple, but the first result is if we take, in general, if we consider the birational sequence, I told you this birational sequence Sn plus 1, if I just recall you, alpha n minus 1n, alpha n minus 1, blah, 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 alpha 1n to alpha 1. And I want to consider the vector partition problem associated to this vector partition. And then the answer is the following theorem. So I know what is the Grobner cone, and I can give all the facets description of this Grobner cone. These facets are exactly of two types. The first type is 3-term, and the second type is 4-term. And moreover, in this case, I also know what is the reduced Grobner basis. And that's how one proves all the things. And the important thing is everything is explicit. There is a cone explicit. And then if I look at this cone, this is an open cone. So usually you get open cone, but if I close it, then I will get, if I close it, this cone will have an n-dimensional linearity space. And if I quotient, because I don't like linearity space, so I quotient out. After the quotient, I will get a simplicial cone of dimension n minus n, because there are only n minus n inequalities, if you count them. So this is the quite standard. Now I want to give you some a little bit complicated example, which is S4, because S3 is too easy. So S4, what are the inequalities? These inequalities are W11 plus W22 larger than W12, W22 plus W33 larger than W23, and I have to think W12 plus W23 is larger than W22 plus W13. Okay. So you see there are only 3 inequalities. And there are 3-dimensional linearity space, and this is a simplicial cone. So for simplicial cone, we know that later we will discuss this simplicial cone, because this is a very interesting cone, appears in representation theory and cluster theory and many other places, if I have time in the end. Okay. So this is the first part. And later, this cone C larger of I will play the role of the cone C I explained in the very beginning. So this is the first step. The cone C comes from some Grobner theory. And now the second part is I want to go to tropical. Okay, this is the second part, the way to tropical. So then in this part, the goal is to explain you how to define this map alpha for any point in this cone. See, in this cone, I want to give a degree to Prequel coordinates such that the initial ideal is a prime binomial ideal. Okay, now let's how to do this. The way of doing this is via some Newton-Alkounkov theory, or you also sometimes call it Hovansky basis. So the idea is that why this is called birational sequence, because birational sequence give you birational parameterizations, and birational parameterization give you valuations. And this is the idea. So to really explain this idea, I want to recall some definitions. I think this is clear for all of you, but I take this opportunity to fix some notations. So I will recall what are the Prequel coordinates quickly. Okay, so okay, I should ask whether there are questions so far on the first part.
I'm sorry, could you quickly repeat what was the ideal I?
The ideal I is the kernel of this polynomial map. This is the polynomial map, or here. I is the kernel of this map.
Great, thank you.
So this looks like you have this vector partition problem. You want to write a vector into different way of the vector given vectors. These are the minimum. These are not minimal, but the reduced Grobner basis is a minimum move. How to go from one to the other. So, okay. Are there further questions? Okay. So if no question, I will continue my Prequel coordinates. Prequel coordinates. So first, I want to fix this notation of n+1 choose k. This means that k element subsets in this n+1 alphabet. And then I want to fix my standard basis of Cn+1. I call it E1 to En+1. And once this basis is fixed, we have a linear basis. I will write here C basis. If I fix the basis of Cn+1, then I will get a C basis of this wedge product. It's exactly given by this wedge product. And here, my convention is that when I write I is I1 to Ik, I always assume that I1 is smaller than Ik. So then I don't bother with all this plus minus one stuff. So this is the basis. And what are the Prequel coordinates? The Prequel coordinates are exactly the dual basis of this basis. So it's in the wedge K of Cn+1 dual. Okay. So later, the idea of tropical flag variety is to give all these Prequel coordinates a degree. And now the degree is something, just a degree is a number. But as I said, the number is too arbitrary. So we don't really want a number. We want many numbers. And from this many number, we want to produce one number. This is somehow the idea of this evaluation. So I want to explain. So how to give Prequel coordinates many numbers. So I want to explain how to, from a birational sequence, give a rational parameterization of these Prequel coordinates. Okay. So here's the setup. So here I fix my favorite birational sequence, beta 1 to beta n. And of course, here is my example sheet. My favorite one is S3, is alpha 2, alpha 1, 2, and alpha 1, my birational sequence. And now I fix some I. It's a Prequel, because I want to parameterize the Prequel coordinates, so I give an index I. And I will define Fi is a polynomial defined in this way. I think this is it's not very familiar with you, so I think I will do one example so it becomes clear after you see the example. So first, I want to compute this part. So let me do it. Previously, we have already computed this multiplication here. So it is 1, 1, 1, T3, T1 minus T2 plus T1, T3, 0, 0, 0. And then I want to apply it to E1 wedge EK. Here there are two possible K. K is 1, K is 2. So I want first to act on it on E1. So if I act it on E1, so all of you know how to do this the first semester, first week, linear algebra. So you're gonna get E1 plus, I don't know, I think I computed it. Now I need to find it. Yeah, it's here. T3 E2 plus minus T2 plus T1 T3 E3. Okay, just first column. And then if I do it on E1 wedge E2, which means that I will, if this guy acts on E1 wedge E2, which means that I want to take the determinant of the 2 by 2 minus of the first two column. So I will get E1 wedge E2 plus T1 E1 wedge E3 plus T2 E2 wedge E3. So if you compute, you get this. Okay. And now I want to see what I get in this formula, what I get as Fi. Fi is I act the Prequel coordinates on my linear combination. Since this is a dual basis, it's very easy that F1 is 1. F2, I just mean 1 means this subset of I. F2 is T3. F3 is minus T2 plus T1 T3. F12 is 1. These are just these coefficients. So F13 is T1 and F23 is T2. Okay. So then this is this definition here. So now I get for any Prequel coordinates, I get a polynomial. In general, this is a polynomial. It could be, if you consider some complicated cases, it could be rational, but here it's always a polynomial. So this is the reparameterization. And you see this reparameterization looks quite nice because from here we can define a valuation. Because they still satisfy the Prequel relation if you look at this this parameterization. Okay, so let me fix valuation. Here I still use my favorite lexicographic ordering. You can, in general, you can take arbitrary. This doesn't matter. And here I take my lex, and then I will define a valuation v larger. It's from this polynomial ring to n to the n. In general, it's from the field of rational, the rational functions, but here I simplify things I can. And if I take a polynomial f, I will send it to the minimal term with respect to larger. So this is a change because previously I take max, here I take mean. I personally understood this as in the Newton-Archenkopf and the tropical, there is a mean-max change or a sign change, as you can see from different work by Kumas-Cave and Grassmannians. Okay, now let's continue this example. What I will get as valuation, this guy I will get 0, 0, 0, and this guy I will get 0, 0, 1. This guy I will get 0, 1, 0. This guy again 0, 0, 0. This guy 1, 0, 0. And this guy will give me 0, 1, 0. This is my valuation. So for any Prequel relation, for any Prequel coordinate, first step is to give it a tuple of numbers. And then I will go from this tuple of numbers down to a number. And how to do this, I just take the inner product. So that's the next step. Before that, I need to tell you what is the tropical flag variety. I think all of you know that, but still, it's always nice to recall it as I'm not really a tropical expert at all. Okay, so let me take the T as the union of all possible Prequel index of Prequel coordinates. And then I will denote by PL n plus 1 is the Prequel ideal defining my flag variety in the product of, okay, here I should be little bit careful. I would not like to say that this is a product of Grassmannian, rather than it's in the product of projective space of diameter k, c, n plus 1. This is, I should be a bit careful, because I still need the Prequel relations for Grassmannians. Anyway. And then we know that this Prequel ideal sits in this polynomial ring, and the Prequel ideal is explicit, but it's of mysterious. So there are many work on the Prequel ideals, but anyone who wants to deal with these ideals will encounter many complicated problems, because they are because of the combinatorics mainly. Okay, now I want to define for you what is the tropical flag variety in my head. So this for me are the, okay, so here I should change a typo. This is T, it's a curly T. So these are the weight vectors, which mean I give all Prequel coordinates some degree, such that the initial ideal of the Prequel ideal, so I don't need to introduce the initial ideal in this seminar, contains no monomials. And then I need, because there are some, this is the multi-projective embedding, so I don't want to fall into this problem. So I artificially put all the the weight of P1 to K to be 0. Because this is coincides with my my definition here, because if I take P here, all these coordinates, all these parameterizations are always 0, 0, 0, because I took this guy as a highest weight vector, something like that. So this is, for me, a very natural assumption, because usually you quotient it out, but okay. Now I can tell you that this is from the general results of Vieri graphs. This is a pure polyhedral fan in R of the curly T. Sorry, I have to change it to the curly T of dimension big N. This is a general theory. And now how I define my map alpha. My map alpha will, from this cone C larger of I to the tropical flag variety, it just take a degree vector, or this D is a vector in this cone, and I will get some degree for the Prequel coordinates Pi, where this degree is nothing but this inner product. So one moment. Okay. This inner product, but here I need a minus. For some reason, I need a minus here. This for the coherency. Okay, so maybe I give you one example to see how this works. Okay, but now I think it would be better that I do it here. This example will go to this region, because I have already a computation there. So for example, I take my D is I don't know, a 1, 0, 1 in this case, because then W1 plus W3 is larger than W2. And then I will get W1 is always 0, which is W12, and W2, it is T3. So T3, it has the, this is T3, it has parameterization 0, 0, 1. And I take the inner product of this vector with this vector, I take the minus, so it gets degree -1. And similarly, W3 gets degree 0, and W13 gets degree -1, and W23 gets degree 0. Okay. And now if I look, this is the degree. If I look at my F flag 3 Prequel relation, it has a principal there's only one relation, P1, P2, 3 minus P2, P1, 3 plus P3, P1, 2. Okay, and then I will plug in these degrees. So this guy gets degree 0, this guy gets degree 0, this guy -1, this is -1, this is 0, this is 0. So this term has degree 0, this has degree 0, this has -2. So initial W of my Prequel 3 is generated by P1, P2, 3 plus P3, P1, 2. So you get a binomial ideal, so you get a toric degeneration, you get everything from this construction in this small example. Okay, this is the construction, what is the cone C, what is the map alpha, and now I'm able to state the theorem. The theorem is due to Evgeny Feigin, Jason Fourier, Igor Makhlin, and myself. It's 2019. But the proof was representation theoretical, and here it's, if you read the paper, it's the different approach than this approach I present today. But the theorem are the same. So the theorem says that the map alpha is associating this from here to here. This is the linear map, and then this is not the part, but the part is next. It sends the closure of this cone bijectively to a maximal prime cone in the tropical flag variety trop Fn+1. So prime cone means that you take this cone, there is associated, you take any weight vector in the interior or relative interior of the cone, there is the initial ideal. This initial ideal is a prime ideal. So here we get the facet description of one maximal prime cone in the tropical flag variety. Why this is explicit? Because C larger I, as you have seen, this is explicit. You know all the facets in detail. And this map alpha is also explicit. This map alpha is also very explicit because this valuation are explicit. We know we have a combinatorial, or even not combinatorial, it's just a direct formula for any Prequel coordinates how to write down this valuation image. So which means that this map or this cone, maximal prime cone, is explicit. And how explicit it is, I'll show you one example this is a running for the running case. So let's take our running example. This C larger I, this Grobner cone, if we close it, we get D1 plus D3 larger or equal to D2. And now what is the image alpha of D? So as if you compute, because previously I give the example 1, 0, 1, and then if you plug in D1, D2, D3, you're gonna get 0, P1 is degree 0, P2 have weight D3, P3 have weight D2, and so on. And now I can write down this maximal prime cone in the tropical flag variety. It is exactly given by W3 is W23 and W2 plus W13 is larger than equal to W3. Of course, there are two things are 0, but this is already in my definition. And we get an explicit description of this maximal cone. And so before going to the next part, is there any questions or remarks?
Yes, I have a question. Actually,
Please.
can you retrieve the other maximal prime cones by, I guess, varying the directional sequence or maybe the order?
Yes. This is something. This is why it's called working in progress. So we know in other examples how to get some other maximal cone, let's say tropical maximal prime cone. For example, we can get one for the Gerfond-Zettling. we also know the explicit facets of that cone. This recovers a result by Igor Makhlin. And of course, there are some other situation we can also get such a cone. But the thing is, since the problem is really we need some property called Minkowski property, because the flag variety in the definition of the tropical flag variety, you always embed into the product of Grassmannians, which means that you have to have some property on this birational sequence to how to say to make it how to say okay. So okay, I should not say that much, but it's just we can do it for other birational sequences, and even this birational sequence, but with different ordering. And one question maybe I ask the tropical audience is that I don't know, but is there any way, if you know the facets of one tropical maximal prime cone, can you jump to the other? In the Grobner fan, you can walk crossing, but in the tropical world, it's although connected by in codimension 1, but is there any algorithm or things to do walk crossing in the tropical? Okay, this is my question, but I'm not expecting a quick answer. Is there any further questions? Okay.
I have a short question.
Yes.
So, is there anything, let's say, special about this precise cone that you stated the theorem for? Is it a representation theoretic?
Yes.
Or is it known from there somehow?
Yes. This what I want to say in the remarks.
Ah, okay.
Okay.
So I will shut down.
Yeah. Okay. So let's start with Chris' question. Okay. So the first remark is about Chovansky basis. So you may think how to one. Okay, so this. Okay. Okay, thanks, Dan. Yeah. So let me explain you how this theorem is proved without using explicit representation theory. The theorem is can be proved using Chovansky basis and subductive algorithm. The reason is the following. So the first thing is we say we can extend the valuation V larger to a larger one, which is called V larger tilde, which is from this C of T1 to Tn, kick out 0 to here I should say n to the n cross n to the big N, because previously it's just n to the big N. Here, this one is the multi-degree of the Prequel coordinates. So I can extend it. So why this is interesting to extend it? The extend it is the following theorem. This theorem is I should say it's a consequence of many different results. Essentially, this is first is by Feigin, Fourier, Littelmann. And by Kirichenko. And also one needs the Fourier, Littelmann, and myself. One combine all these works, one can prove the results saying that I should how to the set Pi, all the Prequel coordinates form a Hovansky basis of from Hovansky of this homogeneous coordinate ring. Which just means you take this pi and quotient out by the Prequel with respect to this extended valuation. So this is the key point of the proof of this the previous theorem, because once you know that you have Hovansky basis, then you can run this subductive algorithm to starting from the initial term and to produce more terms. And then when you run this subductive algorithm, you will always producing things which are having larger degree because of this C larger of I. This cone will tell you that you go further subductively, then the degree is increasing. That is the key point of this proof. So, and this is the relation to the Hovansky basis. And another thing I want to say is, what is this cone? How many minutes? 3 minutes? So, okay, so then I can say something about this cone. The cone, C larger of I bar. And this cone appears in many places recently in different area. So the first, it appears in the non-commutative Grobner theory of quantum groups. With respect to its PBW, a quantum PBW generator. So this is essentially the work by of Fourier and Markus Reineke and myself last year. And then it, secondly, the phase lattice of C larger I closure. So in this case, it's Boolean, since this is a simplicial cone. And is the lattice of something called exact structure of the category of Dinkin-Quiver representations. And this is the joint work with Misha Gorsky. And next, this one also appears in cluster mutation and G vectors. And I don't know who first did this, and also I don't know who really did this, but I know this is true because the cluster, the references in cluster theory is just blowing up. So I didn't check the history to attribute this result to some people. Up to my knowledge, it's already in the paper of Keller and Gardejo and Keller. But anyway, this is the second remark. And the third remark I want to make, maybe I want just to orally make it, because now you have this maximal prime cone, and from this maximal prime cone, you always get a toric rarity or toric degeneration. And you may ask, what is this toric rarity? And this is the toric rarity associated to the so-called Feigin, Fourier, Littelmann, Weinberg polytope. So you know there is a very explicit polytope whose associated toric rarity is exactly this guy. And now the last thing, I take 1 minute to say, you see now we have a tropical maximal prime cone, and this cone is a simplicial cone. As a simplicial cone, you have all the faces. All these faces, you can get some variety which is irreducible. And how to describe this variety from representation theoretical or from different other point of view, this is done in joint work. So I just briefly write down this Cerulli-Irelli and Feigin, Fourier, Reineke, and myself, 2017, and also another paper this year. So I just want to say one sentence. Many of the faces are of form. What is the form? The form is the variety associated to some faces are of this form, V1 to Vn. These are in product of Grassmannians, such that Vi, previously we asked Vi is included in Vi plus 1, then this is a flag variety. And now we're not asking that easy. We ask some Fi Vi is included in Vi plus 1, where Fi is an endomorphism of Cn plus 1. It's a matrix. And many of the faces, how many? There are 2 to the n, many of faces are of this form. And these guys are called linear degenerate flag varieties. Okay, and that's the last remark I want to make here, and I will stop here. Thank you for your attention.